Hello, I'm Mingyu Wang from Multi-Robot Systems Lab at Stanford University. In this talk, I will present our paper, Game-Theoretic Planning for Risk-Aware Interactive Agents. This is joint work with Nigar, Adrian, and Matt. The motivation of this project is twofold. Firstly, uncertainties are intrinsic to many robotic systems. Robots may subject to disturbances, uncertain perceptions, etc. In driving, the future trajectories of other vehicles are also uncertain. Thus, autonomous systems need to consider the risk associated with their actions. Secondly, in driving scenarios, robots need to be time efficient when interacting with other intelligent agents, such as human drivers or other robotic cars. This means overly conservative behaviors are not preferred. Motivated by these two reasons, we propose to account for uncertainties by using entropic risk measure, which is a well-studied form in risk-sensitive stochastic optimal control problems. To achieve time-efficient planning for autonomous driving, we will use game-theoretic planning framework. Combining these two aspects together, we model the stochastic behavior of interacting agents using risk-sensitive games. We first describe the entropic risk-averse measure, which we will use in this paper. In many stochastic formulations of trajectory planning methods, the expected cost phi is minimized as the objective. However, expected performance is not sufficient when we need to account for risks. We refer to the expectation minimizing objective as risk neutral. In contrast, entropic risk measure optimizes the objective function given by this equation, where theta is a parameter. To understand how this objective captures risk, we apply Taylor series expansion and obtain an expression which includes not only expected cost, but also the higher order moments of uncertainty. In risk-sensitive optimal control, we prefer small expected costs and also low risks. When risk-sensitive parameter theta is 0, the risk-sensitive objective degenerates to the risk-neutral case. When theta is greater than 0, the objective promotes more risk-averse behaviors and more risk-seeking behaviors for negative thetas. This risk metric is preferred due to its ability to tune the level of risk sensitivity and its computational trackability. With this risk-sensitive metric, what if we have several risk-aware agents interacting with each other? Here, we only consider the case with two agents and model the interaction as risk-sensitive games. A known form of this game is linear exponential quadratic game. In iLEQ game, the joint dynamics are modeled as linear Gaussian, and each agent wants to optimize a risk-averse objective function with entropic risk measures. Phi is quadratic in joint state and both actions. For this game, we seek a pair of feedback policies for both agents at a Nash equilibrium. At a Nash equilibrium, no agent can gain by unilaterally changing its policy. For linear quadratic case, a feedback Nash equilibrium policy can be obtained through solving a coupled set of Ricardi equations. We have discussed the linear quadratic cases. However, in driving, system dynamics and costs are generally nonlinear and can be written in a more general form as f and g functions. Nash equilibrium is generally intractable for such games. In this paper, we derive an iterative algorithm to approximate the feedback Nash equilibrium in this case. The algorithm goes as follows. In each iteration, we first approximate the dynamics with linear approximations and the cost functions as quadratic approximations along a nominal trajectory. Then we use the approximated system to solve the backward Ricardi recursions. Afterwards, we use the new solution to forward simulate a new nominal trajectory. The process is repeated until convergence. In this aspect, The algorithm shares a similar structure with iterative LQR method. Okay, let's now move on to some examples. Our first two examples are cross-intersection and a highway merging scenario. Each agent is modeled as an extended unit cycle or a single integrator tracking a path. The objective function is to minimize some risk-sensitive cost function, consists of three terms. The first one is tracking a reference trajectory. The second one is penalizing control inputs to the system. And the last one is collision avoidance cost, which penalizes dangerous distances between the two agents. The right figure shows a visualization of the collision avoidance cost. When distance is positive, which means there are no collision, this term incurs very little cost, and the cost increases rapidly as the distance becomes small and even negative. We vary the risk sensitivity parameters of both agents, which would lead to two different interaction outcomes. In the top row, the green agent has a higher risk sensitivity, which means it is more risk averse. And through simulations, the green agent yields more to the other agent. In the bottom figures, we use the same starting configuration of agents, but instead use a higher risk sensitivity for the red agent. We then discover that the red agent will yield more to the green agent. The induced behaviors are very intuitive and human-like. Next, we compared the algorithm to some other existing methods in both intersection and merging scenarios. Here, we first compare with risk-neutral games, which is solved by iterative ILEQ game formulation. The x-axis here is the level of uncertainty in simulations, and y-axis is the minimum distance between the two agents. We ran 150 trials for each case, and the results are plotted here. We can observe that for risk-neutral games, which is shown in black line, the minimum distance does not change as the uncertainty increases. In other words, the risk-neutral policy is indifferent to noise. Whereas in risk-sensitive cases, as in green and orange lines, the minimum distance increases as the uncertainty increases. This is preferred behavior, as we want to maintain a higher safety level if we are unsure about the future trajectories. Next, we also compare with non-game-theoretic motion planning. In the baseline case, each agent regards the other agent as non-reactive obstacle and solves the optimal policy instead of a Nash equilibrium. We again ran each case for 150 trials. As we vary the risk sensitivity of layer 2, we can see that the proposed algorithm in orange consistently reaches to goal state with less time, compared with non-interactive planning agent, which is represented in green. This shows our algorithm is more time efficient. So let's now move to another example, which is entering roundabouts in Carla Simulator, which is a high-fidelity autonomous driving simulator. One of the agents starts in the circle, and the other agent enters the circle from the right. We compare the results with non-game theoretic planning, and our algorithm achieves much better time efficiency, as in orange. Finally, we also confirm through simulations that the relative risk sensitivity instead of absolute risk sensitivity of two agents determines the interaction outcome. We first look at a high-level behavior, which is yielding. We use 6 different theta values for agent 1 and 2 and run simulations for each pair of values. Simulation results show that as the risk sensitivity for one agent increases, the probability of it yielding also increases. This is expected, as the more risk-averse agent would prefer to slow down and wait for the other agent to pass first during an interaction. Moreover, when the two agents share the same theta value, the percentage of yielding is approximately 50%, as indicated by the diagonal terms. as the relative risk sensitivity increases towards off-diagonal terms, the yielding behavior is more certain and easier to predict. We then look at the minimum distance. The mean distance increases as either agent becomes more risk-averse. This is shown by the change of value in each row towards the right and each column towards the bottom. When both agents are risk-seeking, it leads to small mean distances, as shown on the top left corner. And safer behaviors are observed when agents become more risk-averse towards bottom right. To summarize, in this paper, we model the interaction between risk-aware agents as entropic dynamic games. We then derive an iterative algorithm to approximate the Nash equilibria of such games. Then we conducted simulations on challenging scenarios such as merging and roundabouts. From these simulations, we observed that relative risk sensitivity between agents determines the interaction outcome. And the proposed risk-sensitive game-theoretic framework is more time efficient than if game interaction is ignored, or safer than if risk sensitivity is ignored. Thank you for your attention.